Good morning. Welcome to the third day of the Centennial Conference in honor of Richard Feynman. I'm Yong Yi Hao, Assistant Professor of Physics at NTU. It's my great pleasure today to introduce our first speaker, Maria Spiropulu, Professor of Physics at Caltech. Maria is a renowned experimental particle physicist known for her pioneering searches for supersymmetry and extra dimension at the Tevatron Collider at Fermilab, for her study of the Higgs boson at the Lhc, and for inventing the Razor framework for the discovery and characterization of new physics. Maria has an impressive list of academic achievement, notably AAAS Fellow, APS Fellow, Advisory Panel to the US Department of Energy, and the National Science Foundation. Maria is going to share with us today the state of high energy physics, and please welcome Maria.
Thank you very much. I want to thank the organizers. Before I start my talk, I have a prelude, which includes announcements for the students and follow-up for some things that were said in the previous lectures that I wanted to make some comments. So the first thing I want to say is that the Feynman lectures on physics are now online free. And Caltech and the library at Caltech have made a project of this, so you can go and find them and read them online. The second thing that John Schwartz explained to you all is the Feynman Auditorium at Bridge with the Feynman diagram. This is the upgraded Feynman Auditorium at Caltech. And this is where the Feynman lectures were taking place, and there were plenty of spaces here for various demonstrations. Feynman was teaching there, and all of us have been taught there who passed by Caltech. And all the professors, when they're hired, they are given a few years of Feynman lectures to teach, namely Physics 1. And I have gone through this as well, and it's pretty intimidating because you've got, in the class of the freshman physicists, you've got little Feynmans going around, male and female, and aspiring Feynmans or Feynmans, and at the end of the lecture on Physics 1b, you got a couple of them that come and ask, when we do special theory of relativity, why don't we put time imaginary so that we make the complicated Minkowski space becomes easier? That's what they ask, and then you follow them and you see that that one becomes a string theorist, which has happened. Adam was one of them. Now, what John told you also is that there is a little shrine there with Feynman's picture throwing the strikes. So all the colloquium speakers, when they're there, they have it on their left side as they're giving their colloquium. If they turn like that, they see Feynman over there with his diagrams throwing the strike. And this is, which is this kind of robe that he's wearing? John, you said it was a, who knows what it is, yes. But you see in a Feynman-esque way. I don't know what he's holding here. A lock. It's because of the unlocking of the safes. Who told us about the unlocking of the safes? Danny told us about the unlocking of the safes. Yes, so that's the lock of the unlocking of the safes. I want to show you also the Feynman Computation Center at Fermilab. This is the Wilson Hall, and where we keep all our data centers at Fermilab, we call it the Feynman Center for Computing. More recently, there is at Los Alamos, the Center for Innovation, the Feynman Center for Innovation at the Trinity Drive. It was mentioned in the previous lectures. At CERN, this is the route Feynman. So there is within the CERN site, there is a Feynman route. And somebody said a joke about the penguin diagram, and have you ever seen a diagram looking like Feynman? That's the penguin diagram. Okay, and we're going to talk a little bit about that later. I want also you have seen it either in the museum. No, you have seen it in the museum, and if you haven't been to the exhibit, please go. You have seen the last board of Feynman. The actual board now is is on the Laureate first floor at the office of a mechanical engineer who was an undergraduate student. So we have this board, and it's all engineering on top of this board, the actual physical board. All right, and now I will start. So I will talk about the Higgs and beyond, and we'll see where this road is going to take us. There is a lot of computing at the LHC. There's a lot of physics at the LHC. And we're trying also to figure out roads of computing in order to make it to the next 10 years. And we're getting involved in a lot of artificial intelligence, machine learning methods, not just now, but in the past 30 years in particle physics, because in order to extract signals from backgrounds and analyze the data, because we have huge amounts of data, it's the most efficient way to do computing. I don't want to say much about quantum field theory. This was shown also the stamp for the Feynman diagram. I just want to remind that when we saw from Robert Dycroft that there is one electron and you cut it in space-time, in a similar way when we're talking about the one electron field that permeates the universe, if you quantize that field and you have a quantum field, then you can describe many particles, and you can describe decay of particles. So you don't do quantum mechanics with one particle, but with many. And this is something that it is very important for quantum field theory. And it is the language not only of particle physics, but also of condensed matter physics, as Christiana told us yesterday. And now I want to talk a little bit about the standard model. We have seen it in many various tables and ways. I show it to you here in a way where we see various hierarchies within the particles of the standard model. We usually show it in a flat table, but we do have the leptons and the quarks, which are fermions with spin 1/2, and those start from what we thought were zero masses of the neutrinos, and we were wrong. And, but they have very small masses, all the way to the top mass of 172 GeV. Very important particle, together with the Higgs, and I will explain why those measurements of the top mass and the Higgs mass are creating a puzzle in physics today. And then we've got, so these are the matter particles, and then we've got the particles that are mediators of forces. The photon, the W and the Z boson, those are the electroweak mediators. And then we talked a lot about QCD. These are the gluons, which are mediating the strong force. And all these bosons have spin 1. So what's missing here? Three half. What's missing here in the bosons? 2 is missing. What else is missing in the bosons? Okay, come on. There's 1, 2 is missing. What else is missing? 0, the Higgs. The one scalar we have found. The Higgs is missing here, but we discovered it. There is one puzzle that was mentioned in the various lectures about the matter-antimatter asymmetry in the universe, and it's driving a lot of the physics that we are doing, and a lot of the particle physics that we're doing. So instead of having equal amounts of matter and antimatter as expected, there is a very, very small asymmetry of matter winning over antimatter, and this creates the matter universe that we see. We call this the Parian Asymmetry, and we have not figured out the source of this. We've tried to figure out the source of this asymmetry in CP violation on the quark sector. The quarks mix, and there is a mixing matrix. This is all quantum mechanical, and we have measured the mixing of the quarks and the angles and the CP violating phase, which is telling you how much they mix. And it's not enough to tell you that the universe is matter dominated. So we went and we did these experiments in over the past 50 years. We have been doing these experiments at SLAC, at CERN, in Japan, in Italy to start with, and we measured all these numbers. These are not predicted numbers, these are measured numbers, and we figured out that's not enough to explain the universe we live in. So there is another 50 years program to figure out the lepton quantum mixing, and again, there is experiments in the US at Homestake Mine where the asymmetry of the solar neutrinos was first observed, and there is currently experiments running. Minos has finished, but there is currently experiments running, like oscillation experiments, in order to figure out the corresponding matrix of mixing in the neutrino sector, in the lepton sector. So just one thing that neutrinos, when they come from the sun, from the nuclear reactions of the sun, 8 minutes later, they arrive on Earth, and they start with one flavor we call flavor electron. Electron, muon, tau, 3 flavors. That's a flavor. They start as electron neutrinos, and quantum mechanically, they arrive and they are now 3 flavors about 8 minutes later. So this is, we call those of a definite mass nu1, nu2, nu3, and we call those of a flavor nu e, nu mu, nu tau. And the nu e, you see, is not of a definite mass. And same thing for nu mu and nu tau. So there is this mixing that you can describe them in terms of the components or the eigenvalues, their eigenstates, their quantum eigenstates. So this is the nu1, nu2, nu3, and this is how nu e is an oscillation of this interfering. The big program in the US about neutrinos is a long baseline program where we will be sending neutrinos. Well, we are sending neutrinos now that are prepared in the accelerator at Fermilab, and we send them up in Minnesota in a mine. This is where Minos is, and close by Nova. And in the future, in the next 10 years, we're preparing at the Homestake underground, 1 mile underground laboratory. It's a mine. We used to be a gold mine. We're preparing a huge experiment called Dune. And we will be sending neutrinos there and studying. We will have a detector here to tag how they live, a detector there to figure out how they arrive. They have mixed. They are oscillating quantum mechanically, trying to measure how much CP violation there is in the neutrino sector. And also there is neutrinos, cosmic neutrinos that come from supernova and other sources, cosmic sources that can be measured. So this is a very big program for the next 10 years, which is international also. Okay. So I wanted to say something about neutrinos with regards to Pierre neutrinos. So far, I have been taught that nobody predicted anything correct about neutrinos. No theorist predicted anything correct about neutrinos except for Pierre. So all theoretical predictions have been disproven by the experiments. So I talked a little bit in the museum about the cosmic microwave background and how we have a picture for the universe, a cosmology standard model. Up to now, I was talking to you about the particle standard model. And the cosmology standard model is basically particle physics at around 4% of the mass energy budget of the universe, and the rest unknown. So that's what we learned after about 50 years of cosmic explorations. So, and the unknown, we give it names. We observe it astronomically or cosmologically that it is there. So we observe gravitational effects of this thing that we call dark matter, which is 5/6 of the matter in the universe, and dark energy, which is about 3/4 of the total energy mass budget in the universe. So this part, if they are particles, we don't know what it is. So we observe them because galaxies stay together. There is excess gravity. We could rename this dark matter thing as excess gravity that holds the universe together. And it's very important in order to have large structure formation from the Big Bang to now. Dark matter, in other words, excess gravity is important because the normal matter scaffolds on top of the dark matter. There's many insightful simulations of the universe that give you this. But we hypothesize, our best hypothesis for this is that it is a particle in elementary particle physics. Not in the table that I will show you immediately now, but some other particle. Maybe supersymmetric particle. And as for this, well, 380,000 years ago, this wasn't there. And the universe started expanding in an accelerated form. And so for every second, we are creating a little bit of universe at the edges, okay, with energy, which we measure the energy of that. So this looks like something from nothing. It's very peculiar. It's like a pressure that pulls the universe out instead of gravity pulling it in. Very peculiar. Frank talked about this and about Feynman, and this is a tough problem to reconcile. That's a tough problem, but it's a little smaller. That's a tough problem, and it's a little bigger. Now, we think that smaller problem, that we may have a mirror of this table that is filled with a lot of other particles, supersymmetric particles, which are partners of the particles, partners in spin, okay? We heard a lot about Dirac. Dirac figured out the antimatter, and the last kind of such symmetry that we can have in particle physics is supersymmetry, where the electron is part of a bigger field, where it has a part is the electron and the part is this electron is a partner with not a spin half, but a spin integer. So you've got bosons and fermions being partners. And if they had the same mass, we would have found them. But this symmetry is broken, and we haven't found them. And we're looking for them manically, almost, in the past 30 years. In fact, 10 years ago, I would have given a talk where I would have been pretty certain that we would find supersymmetry first, and then within supersymmetry, we would have found Higgs. Now, there is a symmetry here between bosons and fermions, but it's not really a symmetry. In other words, our world has both fermions and bosons. It would have been nice if they were partners, but they're not partners. They're not partners. I'm going to move to the LHC. This is a slide from about 2 years ago. The LHC, in 2008, we blew it. And we were calling it incident or accident or whatever you want to call it, but it was a soldering 101 problem on connecting the copper on top of the superconducting wires, essentially. And we fixed it within a year. And we had to blow it because there was no other way. We didn't have simulations on what could go wrong because the accelerator physicists and engineers were very sure, because we had built a lot of other accelerators, that we know how to do this. And so we had to commission it, and we recovered pretty fast from the blow. And within the next 4 years, we discovered the Higgs with half the energy compared to the energy that we were supposed to be running because of the accident. And with half the data that we had predicted when we were doing the studies between 2000 and 2008 of how much data we will need in order to discover the Higgs in the mass range of interest. I want you to think that because this will come later. How can we discover it with half the energy and half the data that we had predicted, okay? So register that because it will come back later. The accelerator people, high luminosity LHC, means that you pack more protons per bunch, you collide more protons, you have beams that are much, much denser so that you create more collisions. And since we blew it in energy because of the magnets and we had to run at half energy, the accelerator people, they were very inventive on how to actually pack a lot of protons in the bunches so that we get tons of data. And tons of data means we get a lot of parasitic collisions as well. And we get a lot of the mess of the kind that you saw in the slides of Lance yesterday, and all of this mess can be under control also because we had the work that Trickfield and Feynman had done, and I will show something about that. But we arrived at the kind of design in terms of luminosity, in other words, in terms of how much data we're getting, that was predicted for 10 years later, okay? So more data than designed, less energy than designed. Here it is. This is the LHC. This is an accelerator complex. It works like, doesn't work like you can get the protons and you bring them to the speed of light or close in a ring. You have to go gear first, gear second, gear third, and all these gears are pre-accelerators, small pre-accelerator boosters and linear accelerators. So you have various stages in order to increase the energy and arrive here. Now we are running at 13 TeV, so 6.5 per beam. And the points of collisions are the 4 big experiments. There is about 10 other experiments at the LHC, CMS, Atlas, ALICE that we have ion beams colliding, and Lhc B, which is a B physics experiment, asymmetric B physics experiments, not for pi coverage. But these are the general purpose experiments in order to discover the Higgs. They were built to discover the Higgs. So the total inventory of liquid helium at the LHC is about 130 tons. And about 13 tons per year is the losses. And 9 tons is what we need at any one moment in order to run the LHC. Why? Why liquid helium? Because we need to run these superconducting magnets at 1.9 Kelvin, and the 2 tunnels, you saw at some point 2 tunnels. The 1 tunnel is the feed through for the cryogenics for the magnets. And indeed, the LHC itself is the most complex and the most scaled up machine that humans ever built. This is one of the 2 detectors. This is a compact muon solenoid. If you were to design a detector like that, you would think first which kind of particles are coming out, how particles interact with matter, and there is a BL square law. B is the magnetic field. L is how far away the tracks will go in order to bend. And then you can design your detector to have magnetic field large and big. The L could be small, that's CMS. The other detector is Atlas. You design it to be with smaller magnetic field and it's much larger than CMS. And based on this choice of the magnetic field, you have to choose all the technology for all the various layers of detectors that are going to be capturing the energy of the various particles. So if you have small space, it means that you have to find a material to keep very high energy electrons, but this has to be small. You can't build large calorimeters, for example. And this drives every choice, every technology choice of the detector. And this is another version of this from the other side where you see the 3.8 superconducting solenoid around here, where the tracker, the silicon tracker, which is like a 100 megapixel camera, huge silicon tracker, is inside so that the particles bend. And again, this kind of magnet, you don't make a prototype. It either is going to work or not. So when we commissioned it, we were holding our breaths, but it did work. In the museum, you saw an exhibit of the artist having the two beams. The two beams are, in fact, trains of beams. And here I show you what is the cross-section of where they meet. It's about 13 microns. So we squeeze the beams with the equivalent of optics, which is magnets and electromagnetic fields. We squeeze them and we bring them in collision at about 13 micron interaction point. And the beta is telling you, is a parameter of the optics that is telling you how much the squeezing of the actual particles, how effective is the squeezing of the particles in terms of having more and more collisions. So the design was 50. We arrived in 2016 at 40. We are running now at 30. The smaller it is, the higher is this L, which is luminosity, which is amount of data. Now, we announced the Higgs in July 2012, July 4th, somewhere here, with this amount of data, very little data. And this was a run, the 2011, the 2012, the 2010, which is not here. There were runs at 7 TeV, okay? We went from 7 TeV to 8 TeV to now 13 TeV. So with very little data, we found the Higgs. And this is significant. And as I said, now we are running with beta 30. This is giving you very high number of collisions. In general, the LHC, compared to all the hadron colliders that we have built previously, has had the highest performance, availability, and duty factor. And again, that means we learned a lot from the Tevatron and the previous experiments. So this is a highly non-trivial statement to say the Tevatron was available 30%, the LHC is available at 90%. We are now here. We have finished, well, we are in 2018. We have finished run 2 up to the end of 2017. We had 97 inverse femtobarn. With the 2018 data, we have another 60, and we have exceeded what we were planning to have. Now, in the specific amount of time. Now, I wanted to make the point that the whole history of particle physics, with all its Nobel Prizes and discoveries, we were able to reproduce with 9 months of LHC data. And this is quite spectacular and something to remember, that when the previous knowledge, when you have a powerful machine and you are prepared, you can go very fast. You can progress very fast. And this is the probe of the LHC. This is the standard. This is where standard model in terms of scales in meters. This is the whole universe, which seems to be excessively useless in terms of how big it is. And this is the useful part. This is also useful. The neutrinos are useful. And again, for the neutrinos, everything that we have ever predicted, except what Pierre predicted, was wrong. But the LHC is extending the reach, as you see here, okay? And in this little reach that it extended, we found the Higgs. I want to have an interlude here, because Rick didn't get to talk. But if you go to his website, you will find his talks. And he has amazing talks about Feynman. So I wanted to say, the basis of all our Monte Carlo simulations for hadron-hadron collisions, the actual basis from the beginning, and where the big leaps are being made, because you start from zero, so whatever you do is a big leap, is from Feynman and Field. And here is a bunch of their papers that they had. And Rick mentioned the story about the axis of pions yesterday. And he mentioned that Feynman met Cronin, and Cronin told him that the data was showing what they were discussing. And so this is the telegram from Feynman to, let me see where it is. Rick Field Caltech, there it is. Okay, and what does it say? It says, so Cronin, I'm now convinced we're right track. Quick write, quick write, write the paper. And then, I don't know, Feynman, all right. And then Rick in his talks, which you can find here, by the way, he's kept the envelope, and what Feynman followed up. So there are letters from Feynman, and instead of week here, I noticed that Rick pointed out in his slides that instead of week, he pointed week. He had a little spelling mistake, and then impressively he said onward, and he said go ahead and write very fast, basically. Okay. All right. So this is the Monte Carlo simulations from this epoch, all of this. And again, this is from Rick, as you see here. These are the ones that, when I went to grad school, we were working with these ones. That's 24 years ago. These are the ones that exist now, together with Black Hat that Lance showed yesterday. In fact, Lance's is a little bit today, tomorrow, I would say, what he showed, and I will show in a minute there. And all of these have modules that plug in order to try and do hadronization, fragmentation, the parton shower model, which is very difficult. Okay, and these are the kind of calculations that they were producing in order to make all this, and they were inputted in these Monte Carlos. Now the QCD works, it works, and we all know it. This is from the data, the Atlas data that Lance showed yesterday. And the predictions at next to leading order, and next to leading order, and the diagrams that they have been calculating, they have been right on in the high PT regions, okay? And here what Lance also showed you from his slides is how many orders of magnitude the standard model in terms of QCD associated production of everything works. Now we have to measure Higgs plus jets. We have arrived down here where we have TTW, TTZ, we measure TT Higgs, and we are going to be doing differential measurements of associated production of Higgs plus jets. If we found supersymmetry, we would have SUSY plus jets as well. So QCD doesn't go away, it stays there forever. With every new thing that we find, there will be that plus jets. I think this is not a public event yet, so don't tweet it. But this is the highest DiJet event that we have from the LHC. And you can see that it is 7.9 GeV in mass. And it shows you how the LHC can probe over many energy ranges. It's pretty impressive. All right, so let's go to the beyond. And I want to make here a comment, and again, I'm showing something here on the first measurements we had on how we discovered the Higgs. We discovered the Higgs in decays to Z. This is associated with ZH, WH, different kind of initial states and final states, including the top. But initially, how we discovered it was in Higgs decaying to 2Zs, in Higgs decaying to Ws, and in Higgs decaying to 2 photons. And we did not have any connection of the Higgs to the fermions. It was only the bosons. This is how we confirmed between 2012 and 2016 the electroweak symmetry breaking mechanism with that Higgs that gives masses to the W and the Z boson, leaves the photon massless, obviously, and then the program that we have been pursuing ever since then is to figure out what is going on with the fermions, how the fermions get mass. The fermions do not get mass directly, but through the Yukawa coupling, so we have to measure the Higgs decaying to these, to the fermions, and figure out this coupling. So this is a program that we're doing now, and I will show you a little bit about that. But beyond the Higgs, the kind of questions we have, is it the standard model? With all the measurements that we have so far, it looks more and more that this is the standard model Higgs, but is it exactly the way that it is predicted? We don't know. Is it more than one? We're looking for more Higgses. How many more? We don't know. The long-term challenge for the LHC is finding heavy Higgs bosons with non-standard interactions. This is something that is included in supersymmetry, which predicts at least 5 kinds of Higgs bosons, which are different in terms of mass and other properties. The other connection of the Higgs to the beyond is the following. If dark matter is a particle, as we hypothesize, is it connected to the Higgs somehow? The neutrinos, we thought that they were massless. Now we know they have masses. How do they connect to the Higgs? It's not clear. And then, as I said, what is the CP violation origin and the origins of the fermion masses? One extra credit here is if we can connect the Higgs to inflation or dark energy. And that's a difficult one. If we take it out of the box and we do the calculation, it gives us nonsense numbers. This, nonetheless, can describe a multi-decade program on many fronts with new ideas and new technologies. You can develop a program here that will cost $10 billion and build a linear collider in Japan, or another program that will be another so many billions, and you can build other circles in China, and they're thinking about this, or making the circle in Europe bigger. Or you can think of tabletop experiments, or you can think of EDM experiments. So you can think for beyond the standard model in smaller experiments, and there is also where quantum sensors and quantum detection of very faint signals is coming in. This is how we connect experimental high-energy physics, theoretical high-energy physics, and a lot of the new kind of materials in condensed matter physics. I will say a little bit about that later. Okay. Now, just to remind you, if you haven't seen it, it's pretty spectacular. This is what we saw when we unblinded the box of the Higgs on June 13, 2012, a month before we made the announcement. And you can see here the Z boson. You can see some continuum here. This is the data, the points. This is a prediction. The standard model prediction works very well, but this was a standard model prediction without the Higgs, the blue. And then for every mass of the Higgs, we had a prediction how it would look like. So for a mass 126, the red is the Monte Carlo prediction, the calculation plus the detector. And as we were accumulating data, as you saw, we were getting this. And I think 12 June was the time that I saw this data, and I believed that this was, there was something there. And that was my team, part of my team, together with postdocs and students from another 6 universities. In the room, there were about 12 people that opened the box. And then they had to run directly to the spokesperson to say, I was on Skype, and I have the messages from as I was talking with my postdoc on my phone. Very bad language messages of a big excitement. And I say I believe that because the previous data we had was this for the Higgs. In another channel, that is the channel with the top loops. This is how the Higgs gives mass to the photons, namely no mass. It's because it's the loops with the tops are there. And similar loops over there is with gluons, for example. So this is a very difficult analysis. Look how the background is here, the standard model noise, and look how the background is here, this huge signal to noise. We used a lot of classifiers and boosted decision trees in order to get all the variables here optimized in order to tease out this little signal there. And data-driven techniques. And that was the first channel where we saw this blip here. And people who were taught quantum field theory by Shelley Glashow were biased not to believe any of that. So I was skeptical. We reproduced everything in 2016. Here is the Higgs. This is the 4-lepton mass where we discovered it. This is how an invariant mass, so you know that for sure it is. And I will show you now how some candidate events from the collisions, up to the collisions, this is a graphic simulation, and then everything else is the actual detector depositions. This is 2 photons from the Higgs. You see photons are neutral, they don't leave anything on the inner detector, and they leave 2 towers here in the outer calorimeter, the electromagnetic calorimeter. And then all of this is the collisions QCD stuff on the blue, which is the hadron calorimeter. And now we are going to see 4 leptons from Higgs going to the Z boson. And these are, so look at that, they are color orange. The photons were orange also. So can we guess which particles are these? They're not photons because they have tracks. But which particles could it be? Could it be muons? They stop at the electromagnetic calorimeter. So the others were photons. Might they be electrons? They're electrons. Right. So we got in the part of the CMS collaboration that it is US. We are about 30% of the collaboration, and we're about 30% is our fair share on how much we pay. And most of the graduate students, however, 900 of 900 graduate students, most of them are from US institutions. And so we got from the White House, we got a thank you now. We're a little bit less nervous about how much money we're giving you. You did something here. And we got also thank you from Higgs for his Nobel Prize, promptly. I think he sent it, who sent it faster? No, actually, the White House sent us the message faster. He was a few days later, Mr. Higgs. Now, I want to say something about symmetry breaking and complexity, because it was mentioned in the art session 2 days ago by Robert. So if everything is symmetric and there's no electroweak symmetry breaking, the universe doesn't exist. Symmetry breaking means complexification, and unification going backwards means uncomplication or simplicity. But if it's very simple, it's not very interesting. So symmetry breaking and symmetry breaking in every phenomenon is giving you insight on the complexity of the phenomena. The actual symmetry that is there is very beautiful, but the breaking is making things interesting. And you see that Nambu in his lecture, in his Nobel lecture, he made a point to talk about cross-fertilization between the various sciences and specifically between particle physics and condensed matter. So there is symmetry breaking in ferromagnets, in crystals, in superconductors, and in all of these kinds of symmetry breakings, something is, some symmetry is broken and some state comes out. In the case of the symmetry breaking of the electroweak vacuum, the state that comes out is the Higgs boson. And in that case, the quantum vacuum is the medium, okay? In the other cases, it's phonons, it's Cooper pairs, it's other states. So, and this was described by Anderson in an article that he wrote in Science, that more is different, in that complexity makes things interesting, and the quantum vacuum is essentially like a many-body system, and that has inspired a lot of cross-fertilization, indeed, between condensed matter and particle physics. In fact, so much so that in some articles, people try to talk about symmetry breaking and Higgs type of states in various energy scales. So we found at the TeV scale, we found the Higgs. At the smaller scales, there is Bose-Einstein condensates in condensed matter, superconductors, antiferromagnets, and a colleague of mine that we hired a few years ago at Caltech, his name is Manuel Enders, he created some Higgs amplitude mode at the two-dimensional superfluid mode insulator. This is not a massive state. This is like, I don't know, a 20 hertz state of sorts. And he's doing it in a two-dimensional lattice. But there's a symmetry breaking, and the language and how we understand it is very similar. I showed this at the museum as well because I wanted to remind people that the first cosmic event we have in the universe is indeed the electroweak phase transition when the universe kind of becomes massive. Before that, all these are based on very beautiful quantum field theories and other theories, in fact. So this is unexplored experimentally. We are waiting, perhaps, the cosmic microwave background experiments and the gravitational experiments like LIGO now could probe the physics here. It's going to be tough, but they could probe it. What we have is indeed the 10 to the minus 11 seconds. This is the electroweak scale in seconds. And from then on, we have, once we have the massive universe, we have everything according to the Big Bang theory, nucleosynthesis, large-scale structure, etc. All of that works very well in order to have the modern universe. And this is where the astronomers, together with the particle physicists, had created a 20-year roadmap from quarks to the cosmos, where particle physicists and cosmologists and astrophysicists and astronomers work together. So you've got all QCD here, and in fact, it's the plasma, it's quark gluon plasma, and nuclear physics, and you've got then the universe. Now, I want to say something which the Higgs we found, it was predicted, and it was it looks like it is as it was predicted. But the mass that we found it at is creating a bit of an existential problem, or we have to accept that the universe is fine-tuned, okay? And this is what these words are trying to say here. And for that, we were prepared. We were prepared. We had the answer to this story here. We were expecting that we will have supersymmetry, so that the quantum corrections to the Higgs from these loops will be tamed and we will not be talking about these kind of problems, naturalness and all of that. Now, it's very stupid to say the Higgs is unnatural because we measured it. We found it. So if we found it and we call it unnatural, it's kind of stupid. However, what we didn't find is how to calculate all this, what to do with the calculation of all these corrections. And this is all quantum field theory and the heavy particle masses in the quark loops there. And compound it with what I told you, we measured the mass of the top and this mass of the Higgs and the absence of any new physics. Our story was good. If we had supersymmetry, we could have tamed the Higgs. Within supersymmetry, we had good dark matter candidates, and now all this is blowing in our faces. We don't have supersymmetry, so therefore we can take the standard model particles. And the standard model particles that we measured, namely the Higgs and the top, if we put them on the diagram of how we do calculations in quantum field theory, they are telling us something that the universe is unstable, the quantum vacuum that we live is unstable. So now, this was studied in the 70s, in fact, by Rick Field's student, Wolfram, together with Politzer, I believe. And they didn't know the numbers, however. They didn't know the Higgs mass. Now that we know the Higgs mass, we still don't know how the Higgs gives mass to itself and its potential. So if this was the potential that the Mexican hat potential, we can be here. But if the strength of this interaction is distance dependent and depends on the top quark. So the effective potential depends on the Higgs mass, and the self-coupling and the quantum corrections depend strongly on the top mass. This is why we arrive here. But the potential could be like that. So it could be, instead of going up and we are in a safe place here, it could turn around. And then, well, if there's another minimum here and we have quantum tunneling, the universe goes somewhere else, goes in a minimum, in a better minimum. And so that is, that's not the universe will not be as we know it if this is the case. And now this is calculation, and you can ask how long will it take, and theorists will tell you with these considerations 10 to the 111 years, with these considerations tomorrow, with these considerations even now. And so it's mysterious, but we keep paying our taxes because the universe is not going anywhere. I think there's some more mystery here. The reason why I'm saying this is because if you put some new particles, then that all goes away. There's no mystery. But now you're going to tell me, where are the particles? Yes, this is the question. Where are the particles? And this is why we need new physics. We cannot call it the normal sushi that we have been studying it, but we need it in order to have all quantum field theory working. And quantum field theory is working, we know it. Now, whether it works through all the scales of the universe, we don't have reason to assume no. But this is the kind of things that we have to think carefully. Now, I showed you 2016, the Z. Here is the photon again, so this is growing, and here it is the ZZ again, the Higgs in the Z mode. What we do now with these measurements, those measurements, when we made them, we were waiting to have 5 sigma. We were waiting to have enough signal to noise that we can exclaim Eureka statistically and it wouldn't go away, okay? For the other various modes where we didn't have the Higgs to BB bar or the Higgs to tau tau or TT Higgs, these are all the couplings of the Higgs, the strength of the coupling of the Higgs to the particle as a function of the particle mass, and the errors are the different errors that from the modes that we measure them at different confidence levels, statistical confidence level. This is with this amount of data at 7 TeV and at 8 TeV, not even at 13 TeV. And basically at the moment of discovery, if you see who has the smaller error, you know who we discovered with 5 sigma. The rest, there were not 5 sigma yet. There were 2.5, there were 3, there were something like that. Now, if we go and project at 3,000 inverse femtobarn down the road of the LHC, we are going to have exquisitely precise measurements of the couplings of the Higgs with everyone involved. Except, who don't you see here? Mr. Electron. Because we can't, we have to measure the electron in EDMs. It will be very, very difficult. Only if we made an E plus E minus machine, we could, and we make the Higgs there, we will measure it. I talked to you about W and Z and photons. I think it's only with EDMs. No? From, okay. But Higgs to EE, it's not going to be. You don't have luminosity. So EDMs only then? Yes. Yeah, EDMs only. Okay, thanks, Lance. So these 3 are the 3 fermions where we measured the Higgs coupling with 5 sigma also. This is being done now, 2017 and 2018. So we have Higgs to tau tau. Only in CMS, Atlas doesn't have it because they don't have the trigger. So we were clever on how we get all these modes at the trigger level. Taus are complicated. This is the TTH Higgs analysis with, again, different modes of how the Higgs will decay. And this is the Higgs to BB bar just announced about a month ago. While these are best fits, this one and this one, this is the standard model value. And you see we have spread still. So we really need more data in order in order to talk better about this, but we have them right now. So we are exploring the Yukawa couplings of the Higgs with the fermions right now. And the next difficult will be the muons, and for this we might need 300 inverse femtobarn or so, but we are doing it. This is noted here. The Higgs to muon at 15% level. So the name of the game now is to figure out how to do systematic uncertainties and to figure out and to get more data, okay? The key process that I mentioned earlier that we need to measure in order to measure the self-coupling of the Higgs with itself. So what happens in the electroweak phase transition? The Higgs field sets itself on, and the Higgs interacts with itself and gives itself mass. And then the Higgs gives mass to the W's and the Z's, and through the couplings to the rest of the elementary particles, okay? So we need to measure this potential. This is the long plan, the long-term program of the LHC to measure the shape of that potential. And for that, you need to measure the di-Higgs production. It's a very key process in order to do that. We are preparing that, and you see here that the projections is 60% precision on the signal yield, assuming standard model for the di-Higgs, and 40% if we combine 2 experiments, and maybe we can push it down to 25%. This is the other rare process in order to measure the coupling of the Higgs to the muons, and we need a lot of data there. Now, this is showing you, when I said parasitic interactions, when we, Lance showed you yesterday the picture that we have the hard scattering in the middle, and then we have parton shower, and in addition to that, for high luminosity, we have more interactions per crossing than the one hard scattering. So all of that is encapsulated in, we call it PILAB, and it's the mean number of interactions per crossing. So every 25 nanoseconds, we have a crossing, we have a collision, and we have a crossing, and the interactions per crossing are not one. So we don't have one event when we integrate the signals from all the detectors contains integration of signals from up to 60 or 80 interactions. And when we go to the high luminosity LHC, this number will be 200. So the picture is going to be computationally, in order to do the analysis of this data and the reconstruction of this data, is going to be significantly more complex than what we have now. Now, this is, again, the integrated luminosity, and this is up to 2018 up to September. So this was this was about actually end of August, and it was 50 something, and now we are at 60, and we are finishing taking data in about 10 days, and then we collide ions. And after that, we have a long shutdown for 2 years in order to do maintenance of the detectors, of the accelerators, and so on. So we are here. We are at the end of 2018. 2 years is going to be maintenance and upgrades of the accelerator and a little bit of the detectors. And then this is round 3. So in these 3 years, we hope that we will push the data techniques so that we have something little, at least, about the Higgs to mu mu, so that we push the Higgs to mu mu, and then all the way down there, we are going to the Higgs potential, to define the Higgs potential. Now I'm going to move to the SUSY story. So as I told you, and this is maybe 400 of the 800 plus papers that we have written. It's on SUSY searches that we haven't found. So at my introduction, the chair was very generous to say that I have been known for this and that. What I have been known for is not finding what I'm looking for. And it doesn't matter which clever methodologies I do. It doesn't matter it doesn't matter that I did the razor and this and that and that. I haven't found what I was looking for. And I will repeat here the story. We had the story ready that SUSY was very good with the partner of the top, the stop in the loops. SUSY was perfect. It was perfect to solve our problems with the Higgs. And we had the story before we had the Higgs. It's very disappointing that now this is not working. And but this is a theoretical problem right now because we have the Higgs. Nonetheless, for how we search physics beyond the standard model, this is an issue. We have been writing all these papers and searching, and we have been putting limits. And the limits on these partners of the gluons, which are gluinos, and partners of the quarks, which are the squarks, and partners of the gauge bosons, which are the gauginos, are very high. So when I did my PhD, it was one famous theorist, not so famous obviously because I forget his name, it told me that if the gluino is from Michigan, yes, Kane, he is very famous, of course. So he told me that if I exclude 300 GeV gluino, it's over for supersymmetry. It's over. He was sure of that. And so my thesis went to 300 GeV gluino, and in the next years, we worked out, the theorists worked out that we can have natural SUSY, and we can have stealthy SUSY, we can have other models. And so we went from, this is not even in the map here. My thesis in the gluino space, it's not even in the map. It is in the squark maybe. But we have arrived at 2 TeV gluinos, and this is stops. This is 1100 GeV stops. And for the gauginos up to 600, and in different constrained models up to 1 TeV, they're not there. Yes, there are some holes here, you will say. Kinematic holes. We're going to fix these kinematic holes, but they're not there. We're not finding them. What was good about SUSY, if we had found it, is that it had a ready-made dark matter particle for us. It is called the neutralino, the lightest supersymmetric particle, chi 10. We have very good ways to discover it. with missing energy and jet, with missing energy and jets. Missing energy is the lightest supersymmetric particle. It does not interact with the detector. It goes undetected like the neutrinos. We have candidates. We have simplified models with a blob. We have models with mediators. We have very developed supersymmetric models. We have models where the Higgs decays to these kind of particles, to the dark matter particles, invisible decays. We have mediators that connect the dark matter to the normal matter. So this is the coupling of the dark matter mediator, of the dark sector mediator, let's say, to the normal matter. This is to the dark matter. And we're looking also for mediators that can decay visibly in the detector. This is a dark matter mediator, so the dark sector goes in the mediator there. And we're looking at all of these, and I want to remind you, the only way we have seen dark matter interacting with matter is via gravity. I want to remind you this. The first weak interaction that you could imagine to have dark matter interact with normal matter, this is dark, the chi's are dark, or the x is there, is with a Z, and super weakly interacting is with the Higgs that we found. So we're looking for that. We kind of have excluded like that, and I will say something, or it can be also with some other completely exotic force. For what we have done in the dark matter problem, in the dark matter sector, in the sky, via the annihilation of these particles with various satellites, with various experiments like the alpha spectrometer in the space station, the alpha magnetic spectrometer, AMS, or Fermi satellites, or the experiments, underground experiments like the neutrino experiments, but they're looking for dark matter to interact. These are the kind of experiments that would measure the cross-section of normal nucleons in normal matter in various materials. Could be different kind of xenon or other experiments. Could be semiconductor experiments with silicon. Could be squids in order to detect very faint. All of these experiments, and there are many of them, and some of them are in the future here, they have given us lines here that exclude dark matter. If we had, this is here, I want to notice, this is here between 1 GeV and above 1 TeV, 10 TeV. This is all excluded. If the dark matter was interacting via the Z particle, we would have found it somewhere up here with 10 to the minus, this kind of cross-section, 10 to the minus 39. If it is Higgs and supersymmetry, it should be here. A discovery should be here. None of these experiments are finding it. The LHC is coming close to here. And this line here is telling you that at these low cross-sections for these masses, you start seeing coherent scattering, you start seeing neutrino backgrounds, essentially. So you are not having now a zero background experimentation, but you're going to be measuring neutrinos. And so this is a problem then for these experiments, and people have to start thinking on how to deal with this. Now, in various kinds of modes, as I described, dijet modes, boosted dijet, monojets, these are the chi's. Everywhere where is dark matter is the chi. And this is the mediator that, for example, that Z prime that was there. This is the kind of limits that we're putting. From here to here, it's basically resonant production of these digets, for example. They're very powerful. And this is the omega h squared. This is where the preferable values are from cosmology. We're looking everywhere, but we're putting these lines there. So a lot of this type of parameter space we are excluding. If we want to see it together with the dark matter experiments, the underground, the direct dark matter experiments where the neutralino will come and hit a detector, these are the ones that we get from the LHC. And these are some other experiments like Ice Cube and other experiments that are put in this parameter space. This is again the nucleon dark matter cross section, and this is the actual dark matter mass, and it goes from 1 to a TeV. So the LHC is complementary with the other experiments. Now, as of theories of dark matter, a lot. If we move away from the weak scale dark matter miracle, the miracle that says that you will find dark matter and it will be 100 GeV WIMP-like particle, probably supersymmetric, because all the calculations come that, yes, that's good for cosmology, that's good for SUSY, we can do that. If you go away from this, then you start having the zoo, the theory zoo. And what I showed you here is I showed you that we're going down in this direction in order, in fact, let me show again, sorry. Let me show again here, all the way 10 to the minus 50. A question you can ask me is, well, can this go to 0? What does this mean? But we go all the way down there, but you see, these axes I have kept always to 0 and 1. From 1 above, let's say. I haven't gone into very low mass stuff. And what we're doing now is going down to very low mass. So we extend the x-axis backwards so that we can see this. If this was the 1 GeV, going all the way down to the 1 EV and milli-EV and KeV. And you see, together with condensed matter people and people who are doing instrumentation, we're designing which kind of technologies and which kind of signature would it be. Before, the traditional WIMP is with recoil of the nucleon of the dark matter from the nucleon of the particular detector that we're going to use, and you can calculate it. But now if you start having superconducting detectors, superfluid helium, and other processes with absorption, etc., or semi-vile metals other people are thinking of, you start having quantum devices being developed here in order to get very low dark matter. And this is it's work that is happening. The condensed matter people are translating their language with high energy physics people in order to be able to get these devices. So, and this is from Catherine at LBL. So there is a big community report, dark sector candidates, anomalies, and search techniques here. This is from last year, and it's continuing throughout this year. You see here, they even consider from black holes all the way to 2 to the minus, I want to say 11 is down there, yes, this is from femto-EV, okay? So very small masses of dark matter. And I want to make one example because it was discovered by Frank, and it will get him the second Nobel Prize, since we were talking about second Nobel Prizes, if we find it. So I think that was George yesterday that was being nominated with Murray. So the axion candidates are very attractive candidates for dark matter. They would interact very weakly with ordinary matter, and they are very light, 10 to the minus 5 EV. And they are so light that we're thinking them as waves with a frequency of around 5 gigahertz. And if we, with all our cells, let's say Avogadro number of cells, we interact coherently, each our atoms interact coherently, they are coming through us at the rate of 10 to 22 per second. So how do we detect them? How should we detect them? This is a nice demonstrator of how you can detect the faint the faint particle of 5 gigahertz in this kind of an oscillator system. And so you see now all the oscillation has moved here. Even if this was not being at all, it was stable initially. So this is a very nice analog, and this is how people are trying to actually do it. Axion waves rotate B fields into E fields with a very small 10 to the minus 18 degrees is there. This is how the axion interacts. This is the single real photon and virtual photon. And this is the magnetic, you have it in a magnetic field. So you use a very strong magnetic field of about 10 Tesla as the target for this kind of axion dark matter. And the axion wave will drive the electric field of this cavity of a microwave photon, and it's a microwave cavity resonator, essentially. So the size of the cavity must be matched to the frequency or the mass of the axion to get it to do the right swinging in order to be able to measure it. It is almost like tuning your radio, essentially. This is from a simulated axion signal from ADMX, and this is at the megahertz range. This is simulation. Now this experiment, the ADMX experiment, which is axion dark matter experiment at the University of Washington. The noise there, the static on the radio, is basically the thermal photons plus the quantum noise, and so they need very serious refrigeration in order to avoid getting swamped by the thermal blackbody radiation in the cavity. So this is a DOE Generation 2 dark matter project, and here is something that people thought in the meantime, that the quantum limited amplifiers suffer from this 0-point readout noise, which is called the standard quantum limit when the temperature goes to 0. And the quantum noise is 1 photon of 0-point noise per mode in this limit of 0 temperature. Now, if you take the uncertainty principle of Heisenberg, and this is delta x, and this is delta p, and you can also translate it as delta n times delta theta here, and this is still 1/2 h bar. So the phase space, if you rotate it here, the phase space is still 1/2 h bar, but now it's squeezed in the radial direction, and the phase is now randomized. So this is kind of how people thought, and they, in order to go from the cavities that they have into SQL, better than SQL amplifiers with quantum non-demolition single photon detectors. And this has been demonstrated with Rydberg atoms, and it was implemented by Schuster with superconducting qubits. So now the proposal for ADMX is to use superconducting qubits in order to do the experiment. And this is, again, where superconducting qubits, so quantum computing technologies transferred to do particle physics experiments. Now, I want to show you 2 experimental results from the Lhc B that are of note because they are deviating from considerations of lepton flavor universality, which means the lepton flavor universality means that, for example, electron, muon, and tau should behave the same way. And these are charge current, neutral currents. The penguin is here. And they are not from CMS, not from my experiment, but from Lhc B, plus a bunch of other B physics experiments. These are experiments, these are analyses that they have the branching ratio of mesons decays. Here, in this case, it's B mesons to D stars. And if you take all the measurements that we have of this ratio, the standard model is predicting it here, and the measurements are giving you results that are within 4 sigma if you combine all of these measurements that we have from all of these experiments. So they are within these ellipses. So this is a tension in the standard model at the level of 4.1 sigma. And again, you have to combine all of these in order to find it. Here is if you take, basically these are driven by these 2, these are driven by these 4. So you see the difference of the average versus the standard model prediction. And these are the errors. So this has been reviewed for about 2 years because people didn't believe that they thought that it would go away. And it has been heavily refereed, and this is from summer 2018, so recently. And so this has caught the attention of also both Atlas and CMS in case we can go and have enough bees to figure out how we can do these analyses. And we have to be clever at the trigger level in order to verify what is going on there. There is another one which Lance will tell you, well, maybe it's stretchy to, maybe we have to wait before. But there's another discrepancy in this type of ratio with kaons. And this is the value that we get. This is from Lhc B only. And this is all different kind of theoretical implementations. This is what it should be in these theoretical implementations. And the difference here, I think, is because of systematics and acceptance, the difference from 1. But the Q square is basically the mass of the dimuon or dielectron system. And so there is a tension here as well. And I think these are the 2 tensions from the standard model that come from all LHC that are at this moment tantalizing. All right, how much time do I not have? Minus 20. So you have 2 options. Either we do questions now, and then I can tell to people who want to know more about data science, or we play video games with Atari, and I tell you what Demis is thinking. So what do you think we should do, Lars? This was the, discussion. Let's do it. Okay, maybe I can do only the Atari. Hang on, let me do that. I will do it because Demis is a friend of mine and he's half Singaporean. And he is a very inspired young guy who is the CEO of DeepMind. And he has a very great admiration for Feynman, as you see. He thinks that the studies that he's doing in neuroscience and computer science are leading him to understand the brain. And the quote, "What I cannot build, I do not understand," refers in his case to the brain. And he also has a very great conviction that physics and neuroscience are where most of the progress is going to be done in the next years. So I will show you, as I said, he's half Singaporean, half Greek. So I will show you Space Invaders, Untrained. This was one of the first algorithms with deep neural networks and reinforcement learning with reward. So after training, and the scores are on the top, right? It's unbeatable. It's superhuman performance. Totally unbeatable. It's on the one side, the 0 will remain 0 forever. So it plays against the machine, and it's trained basically with raw inputs. The signal is raw inputs, so there's no pre-programming. This is what we said about machine learning. And then I will show you also Breakout. Breakout is funny. Breakout loses after 8-10 games. Then after 300 games, it starts becoming much better. Doesn't lose. And then they forgot to the training. They forgot it overnight, I think. They forgot it overnight training it. And after 500 games, the thing, look what it figured out. It became completely superhuman. When my students at Caltech saw that, they said, of course I did it. But they did it. But this became completely, and it was unexpected from the researchers that they would arrive to this. And this was in the learning curve, the two big papers that they started, the deep learning plus reinforcement learning plus value network plus all these machine learning methods. A lot of them we're using in high-energy physics now in various configurations. But the AlphaGo victory that was achieved with the deep neural networks was not because of the neural networks. The neural networks, as Danny told us, they're old things, but it was because they were combined with reinforcement learning. They had a lot of self-playing where they can use the data again and again, and they had a lot of computing power in order to do this. So I will stop here, and you can ask me more about that if you want, but I think I wrote slides for 3 hours because I had 3 chapters to talk about that I was excited.